In this section, we'll be discussing what's called a Poisson probability distribution. And it's just another category of a discrete probability distribution. So if you look at it, it's going to be very similar on paper, but this one happens to have a really great little formula for us to use. All right, so a Poisson probability distribution is a discrete probability distribution, and it applies to occurrences over a specified interval. And that's what makes it a little bit different. So X is still going to be in the number of occurrences of the event in the interval, and the interval can be time, distance, area, volume, I mean just about anything. But this is the formula that you need to use. So please make sure that you understand how to use the E raised to the power button on your calculator, and everyone has one. You will need the power button as well to find mu raised to the x power, and make sure you know where your factorial button is on your calculator. So these are 3 things you need to make sure that you know so that you can use your calculator to find these. And again, being comfortable with your calculator, very important. There are 4 requirements for the Poisson probability distribution. The first is that the random variable x is the number of occurrences in some interval. The occurrences all must be random, the occurrences must be independent of each other, and the occurrences must be uniformly distributed. And that's really the important one right there. All right, so the mean is still going to be mu. The standard deviation, however, is going to be the square root of mu. So keep that in mind for Poissons. A particular Poisson distribution is determined only by the mean, and it's not going to have an upper limit. So x could be 0, 1, 2, 3, 4, could go on forever. So rather than kind of discussing it, let's just jump right into an example. All right, so there have been 652 Atlantic hurricanes during the 118-year period starting in 1900. Assume that the Poisson distribution is a suitable model. So we're just going to assume that the Hurricane Center has already told us that that's what they're using. All right, so step A. So this is going to be a multi-part problem. A, let's find the mean of the number of hurricanes. All right, so based on the data that we have that's available, there have been 652 hurricanes and over 118 years. So just take your calculator, divide those. It gives us 5.5. And this is hurricanes per year. Okay, so that's going to be your label for that. That is how many on average, right? That is the mean. So about 5.5 hurricanes per year. All right, part B. Find the probability that in a randomly selected year, there are exactly 6 hurricanes. So we need to use that formula and find exactly 6. Okay, so, but in order to use the formula, you have to know the mean, because that's the first part. The mean was 5.5, and you're going to raise that to the 6th power. You're going to multiply that by e raised to the negative 5.5 power. So very important that you know how to put that all in your calculator all at once. And then you're going to divide that number by 6 factorial, right, your x factorial. So you have to know how to use those buttons on that calculator to do all this. So I usually put in this whole thing and then I divide it by 6 factorial and I press enter. And that should give you 0.157. Okay, so the probability that you're going to have exactly 6 hurricanes in any given year is going to be about 15.7%. All right, but you got to know calculator use is going to be really important in this section. So you got to know how to use that calculator. All right, part C. In this 118-year period, there were actually 16 years that had 6 hurricanes. Okay, does this actual result, how does that compare to what we just found in the last? So we found that the probability, so let's go back to the last slide, the probability that we had 6 each year was 0.157. Okay, so if we find an expected value for this, that'll help us understand the problem. So if over 118 years, there is a 0.5157 probability, multiply that, and that should tell you how many years we would expect this to happen. So that's 18.5 years, which is about 18, about it. So that means that we should expect over this period that 18.5 years would have 6 hurricanes per year. So that's not too bad to 16, right? Look at how close that 18.5 to 16. That's not too far off. So that is definitely reasonable, and it looks like our formula worked out quite well. So you make sure that you know how to use that calculator. That's going to be really helpful. Another thing that is helpful about the Poisson is that you can use it to approximate a binomial. So if you don't like the formula for binomials, you can use a Poisson, but it has to meet two different things. You have to have two requirements. You must have an n greater than or equal to 100, and that's usually where most of these you can't, because your binomial doesn't have more than 100 trials. And when you multiply n times p, it has to be less than or equal to 10. So if you meet those two requirements, then you can use the Poisson to use your binomial, to approximate your binomial, and then you can just use that to find your mu. You don't have to go through that big process that we did with the binomials. So let me show you an example. In the main Pick 4 lottery, you pay 50 cents, and you select a sequence of 4 digits. And each digit is any digit between 0 and 9. So you can have repeating digits. So say you're playing 1377 every single day, and it doesn't matter because it doesn't matter what 4 digits you choose, it's the same probability. If you play, because they're totally random, if you play this game once every day, find the probability of winning at least once that year in those 365 days. All right, so a couple things we have to figure out. First of all, we know that n is equal to 365. All right, so we know n is equal to 365. Now, if we want to find the mean, right, find the probability. So we're trying to find the mean, the expected value. We have to know the n and we have to know the p. Now, what's the probability that we win? So let's look at the game a little bit so we can figure that out. All right, there are 10 digits, 0 through 9, for each of these. So 10 times 10 times 10 times 10. So that would be 10,000 different combinations, different possible 4-digit numbers that we could apply. So the probability that we would win is going to be 1 in 10,000. So multiply those two together, and that gives me 0.0365. So if I play the Pick 4 game every single day for an entire year, my expected value, okay, is still only going to be 0.0365, which isn't very good. So let's dive a little bit further. Okay, so we need to find the probability that we win at least once. Okay, so what does that mean? That means we're either going to win 0 times or we're going to win 1 time. So let's find the probability that we win 0 times, because that probably would be a little bit easier. Let me do that in purple. All right, so the probability that we win 0 times. Again, you're just going to use the formula. So our mu, right, we need that for our, okay, raised to the x power, which is 0. So now anything raised to the 0 power is just 1, so that's 1. And then e raised to the negative 0.0365. That will actually give us a number. And then we're going to divide it by 0 factorial. Remember, 0 factorial is 1. So this is just 1, and this is just 1. So really all you need to put in your calculator is that right there. And that gives you 0.9642. So that is the probability that you don't win at all. You never win. So that's, first of all, look at how high that probability is. So probability that you're going to win is pretty small. So if we want to find the probability that we win at least once, and remember we had talked about this before, at least once is equal to 1 minus the probability that we don't win any. So 1 minus that number that we just found says that we have a 0.0358. So that's pretty small. So the probability that we're going to win at least once is 3.58%. Not very big. So that's another reason. Remember, this is why they call the lottery a tax on people who don't understand math. Because if you understood how small a chance you have of winning, you would understand why you wouldn't play. But that being said, if you don't play, you can't win. So that's the problem that comes with gambling. Okay, do you have the tenacity and the self-control to not spend too much on your gambling? Picking up a lotto ticket every once in a while isn't a big deal, but you have a very small chance of winning. All right, so go practice using that calculator, and I'll see you in the next lesson.